Welcome back to the deep dive. Today we're cracking open the architecture that didn't just win a competition. It fundamentally rewrote the rules for how deep learning models should be built. This is the story of how efficiency became the secret weapon for power. We are diving into the architecture codenamed Inception, the winner of the 2014 ImageNet Challenge, but you probably know it as GoogleNet. And our mission today is pretty clear. We want to understand that single fundamental architectural innovation that allowed neural networks to get dramatically deeper, far more accurate, but without bloating their computational cost.
Right.
We're really looking at the moment when smart design started to trump brute force.
And this was a genuine watershed moment. I mean, when we look back, we call this period the revolution of depth.
The revolution of depth.
Yeah.
Yeah.
Before 2014, the consensus was, well, it was simple. If you want better performance, you need a bigger network and more data. But Inception came along and showed that the biggest gains weren't just going to come from scaling hardware.
It was about the architecture itself.
It was about smarter, more complex architectures. I mean, just think about the numbers. GoogleNet got state-of-the-art results in 2014,
Okay.
while using 12 times fewer parameters than AlexNet, the winner from just 2 years before.
12 times. That's a staggering reduction.
Superior performance while consuming a fraction of the resources.
And the name Inception, it really captures the whole approach perfectly. The team explicitly leaned into that internet meme, we need to go deeper.
Right, the movie reference.
Exactly. And the depth here is dual. First, it was a much deeper network than its predecessors, but it also introduced this new complex level of internal organization.
The Inception module.
The Inception module.
Yeah.
It's depth within depth. So let's unpack this. The core problem Inception needed to solve was the issue of scale. You might think, if I want a better model, I just make it bigger.
More layers, more filters per layer.
Right. But that approach hits two pretty serious walls fast. First up, there's overfitting. The more parameters you add, the more likely the network is to just memorize the training data instead of learning generalizable features. And this is a huge problem in fine-grained tasks like ImageNet, where you have to tell the difference between, say, a Siberian Husky and an Alaskan Malamute.
The differences are subtle.
Very subtle. And with too many parameters, the model just starts learning noise instead of the actual distinction.
And that leads right to the second wall, which is just the immediate practical one. Computational expense.
The cost.
Yeah. If you just uniformly increase the number of filters across your convolutional layers, the computation just explodes. It goes up quadratically.
So you end up wasting a ton of computation, right?
You do. You're wasting capacity if most of your weights are near zero or just highly redundant.
Yeah.
You hit a hardware limit or just a budget limit really fast. The theoretical solution, which researchers had been talking about for a while, was actually inspired by neuroscience, the Hebbian principle.
Neurons that fire together, wire together.
Exactly. In machine learning terms, that suggests that you should move from these dense, fully connected layers to optimally sparse ones. If the data itself is sparse, the network should mirror that.
Okay, so if theory demands sparse networks, why didn't people just build sparse networks? What was stopping them?
That's the critical pivot point of this whole deep dive. It's the hardware wall.
The hardware wall.
Modern computing hardware, so your GPUs, your high-performance CPUs, they are incredibly optimized for one thing: fast, predictable, dense matrix multiplication.
They organize blocks of data.
Perfectly organized. But if you switch to a non-uniform, highly sparse data structure, the core efficiency of the hardware just collapses.
So even if you're doing fewer calculations.
You lose all that gain, and probably more because of what we call cache misses. Instead of reading a nice continuous block of memory, the system has to jump all over the place.
It's inefficient.
Massively inefficient. It can even run slower than the dense version.
So Inception was looking for a compromise. They couldn't build the theoretically perfect sparse network because hardware hated it. So they had to approximate it.
Right, approximate the optimal sparse structure, but using the dense, predictable components that hardware loves.
Getting the best of both worlds. And that brings us to the centerpiece of the whole thing. This is where the ingenious design really takes center stage, the Inception module. The whole idea was to find the best local construction for processing information and then just stack that construction over and over again.
Exactly. And critically, that local construction had to handle input features at multiple scales, all at the same time.
What do you mean by multiple scales?
Well, think about an image coming into the network. At any given layer, some features are very local, like a sharp edge. Others are broader, like the corner of a house.
So you need different size windows to see them.
Precisely. So the naive Inception module, it tackles this by operating in parallel. It combines different filter sizes. A 1x1 convolution for very local features, a 3x3 for regional features, and a 5x5 for broader context. And because pooling is so important in CNNs, it also includes an essential parallel max pooling path.
So the network isn't forced to choose one view. It gets every perspective at once.
Exactly. And then the outputs from all these parallel paths are just concatenated, literally stacked together to form the input for the next stage.
And the network just learns which scale is most important at each depth.
It figures it out during training. And logically, as you get deeper, the features become more abstract, less spatially concentrated.
So you'd expect to see the network rely more on the larger filters, the 3x3s and 5x5s, in the higher layers.
That's the idea. The ratio should shift.
But wait a minute, we just talked about the problem of computational explosion. If we run 4 parallel paths and then we concatenate all the results, especially deep in the network where the filter counts are already huge, doesn't that concatenation immediately cause a gigantic computational blowup in the next layer?
You have hit the nail right on the head. That was the immediate, obvious, unavoidable big problem.
We've just recreated the width problem we were trying to avoid.
We have. Every time you merge those results, you dramatically increase the number of output filters, and you set up this unsustainable expense for the layer that follows.
So, what was the trick? The efficiency hack.
This is the true stroke of genius in GoogleNet. It was the judicious application of dimension reduction, using the surprisingly powerful 1x1 convolution.
The 1x1 convolution.
Yeah.
It just looks at one pixel at a time, right? How does it stop a computational explosion?
It's the unsung hero of this whole architecture. It has 2 critical jobs, and the key is where they put it. They placed a 1x1 convolution before the expensive 3x3 and 5x5 convolutions.
Before them. So it's not for feature extraction in the same way.
Not primarily. Its most critical job is to operate across the channel dimension, the depth. By using a limited number of 1x1 filters, you can drastically reduce the number of input filters before the heavy 3x3 and 5x5 operations even start.
So it acts like a strategic data throttle. You're shrinking the data volume right before the most expensive operations.
Precisely. They're often called bottleneck layers for exactly that reason. They shield the next layer from a massive number of inputs. And their second, simpler role is that they also include a ReLU activation, so they inject nonlinearity.
And that one clever architectural trick is what let them build so deep?
That's it. That 1x1 bottleneck is what allowed GoogleNet to have 22 layers with parameters, almost 100 total building blocks, while staying within a tight computational budget of about 1.5 billion multiply ads.
It was an approximation of that sparse ideal, but built with hardware-friendly parts.
Amazing.
Okay, moving on to the practical side. You can design the greatest architecture in the world, but if you can't actually train 22 layers effectively, it's just a cool idea.
Absolutely. The training methodology has to keep up with the architecture. And let's start with the basics they relied on. The activation function.
Rail.
Every convolution used the rectified linear activation, or ReLU. This function, just fx equals max of 0 and x, is so simple, but it revolutionized training speed.
And its main advantage was getting around that saturation problem that you'd see with older functions like sigmoid.
Right, that's exactly right. The sigmoid function squashes everything into a tiny range between 0 and 1. So if your inputs were too large or too small, the gradient, the signal for learning, would just become 0.
The vanishing gradient problem.
The infamous vanishing gradient problem. Your neurons just die. ReLU avoids this because it doesn't saturate in the positive region. And they found networks trained with it could converge up to 6 times faster.
But still, even with ReLU, 22 layers is deep. How did they make sure that gradient signal could even travel all the way back to the start?
That's where they introduced a really clever GoogleNet-specific innovation called auxiliary classifiers.
Okay, what are those?
They attach smaller, separate classification networks to a couple of the intermediate layers, specifically Inception 4A and Fortis. Think of them as little side classifiers.
So they're making predictions from the middle of the network.
Yes. During training, these auxiliary networks also calculate a loss. They're essentially saying, hey, based on what I can see right now, from the middle of everything, I think this is a Siberian Husky.
So they're providing mid-course correction signals.
Exactly. It's a technique called deep supervision. It forces the network to learn to discriminate earlier. You had that auxiliary loss, weighted lightly to the main loss, and it just boosts the gradient signal all the way back.
And then you get rid of them for the final model.
Completely discarded during inference. They're purely a training aid.
That's an ingenious piece of engineering. And even with all this, the sources show they still relied on traditional regularization methods.
Oh, they had to. Dropout was still essential. Even though they got rid of the huge, overfitting-prone, fully connected layers from older models, they still needed dropout.
To prevent features from co-adapting.
Right. It works by randomly setting some neurons to 0 during training, which forces the other neurons to learn a more robust, redundant representation. You're basically training a massive ensemble of slightly different models all at once.
They also leaned heavily on data augmentation.
Very heavily. All the standard techniques. Horizontal flips, random crops, random scales, color jitter. But they were incredibly aggressive with it at test time.
What did they do?
To get their final prediction, they would take 144 different crops of a single image corners, center, different scales, mirrored versions, run all 144 through the network,
144.
and then average all the softmax probabilities to get the final answer. That brute force averaging gave them a final significant boost in accuracy.
Wow. Okay, and finally, let's touch on weight initialization. With a 22-layer network, keeping the signal alive must be a delicate balance.
It's mandatory. If you initialize the weights too small, the activations just go to 0 and the network dies. If they're too large, they explode and you get instability.
You want the variance to stay consistent, layer to layer.
That's the goal.
Yeah.
And the solution here was the MSRA, or Kaming initialization. It dictates that the standard deviation of the weights should be proportional to the square root of 2 over d, where d is the input dimension of the layer.
So as the layers get wider, the weights get proportionally smaller to compensate.
Exactly. It keeps the whole system balanced all the way down.
Okay, section 5. The impact. It was immediate. GoogleNet was the clear winner of ILS-VRC 2014.
Undisputed. Best classification results with a top 5 error rate of just 6.67%.
It really redefined architectural design, but the story of depth, it didn't end there, did it?
Not at all. GoogleNet was followed almost immediately by ResNet in 2015, which solved an even more fundamental problem related to depth.
That's when we started seeing networks with over 100 layers, even 150 layers.
Exactly. And when networks got that deep, a weird thing started happening. A deeper network, say 56 layers, would actually perform worse than a shallower one, like 20 layers.
And not because of overfitting.
No, the training error itself was higher. It was a pure optimization failure. It was just too hard for the algorithm, for SGD, to learn a simple identity function, to learn to just pass the input straight through a layer if that was the best thing to do.
And ResNet's solution was to have the network learn the difference, the residual.
Precisely. They introduced the residual block. Instead of trying to learn the total mapping h of x, it learns the residual mapping, which is f of x equals h of x minus x. And it's dramatically easier for an optimizer to learn that f of x should be 0 than to learn h of x should be x.
And that unlocked truly ultra-deep networks.
Built on the shoulders of the efficiency gains that Inception pioneered.
And the big practical takeaway for you, the listener, is how all of this enables transfer learning.
Right.
The idea that these massive models trained on ImageNet, they learned generic feature detectors in their early layers, edges, textures, corners.
The building blocks of vision.
So you can just freeze those early generic layers and only fine-tune the later, more specific layers for a totally different task, like identifying tumors in X-rays or cracks in asphalt.
It's the essential shortcut in modern machine learning. It saves weeks of training time.
So to wrap this incredible deep dive up, let's just revisit the dark art of training. Hyperparameter tuning. The sources repeatedly emphasize that you should always use random search over grid search.
It's so much more efficient. Grid search wastes a ton of time exploring useless parameter dimensions. Random search, just by picking values randomly, is far more likely to thoroughly explore the parameters that actually matter.
And for learning rates.
If you're ever tuning learning rates, just remember that the range that works best for these huge networks is often tiny, usually somewhere between 10 to the minus 1 and 10 to the minus 5. Testing that range is the absolute minimum you need to do.
The ultimate lesson from GoogleNet, then, isn't just about a 2014 competition. It's that the theoretical goal of moving towards sparse, refined architectures, it's actually feasible.
It's feasible and it's incredibly useful, as long as you find clever ways to work within the constraints of modern hardware.
And the final provocative thought here is, if human engineers could approximate this optimal sparse structure with things like one-by-one convolutions, what happens when we build systems that can automatically construct these optimal, refined, and sparse structures on their own?
Finding those same kinds of efficiency gains, but in totally different computational domains.
That feels like the path forward for all high-performance computing.